So now our next speaker is Manas. Hi, Manas.
Hey,
Hi.
you
So
can hear
good
me?
afternoon. Oh, yes, I can hear
Perfect.
you. So, okay, let me give a brief introduction of Manas. So Manas did his PhD from Heidelberg University and GSI Darmstadt, Germany. Then after that, he did postdocs at various places. And then later on, he took up a position at IACS, Kolkata. Then he moved to National University of Singapore. He's there since 2012. He has a lot of interest in precision spectroscopy and the application of those for fundamental physics. So today he will be talking to us about exploring a single qubit space for sensing and quantum machine learning. So let's hear in more detail from Manas. Yes, over to you,
Thank,
Manas.
thanks, Dilip. Thanks for the nice introduction. And I would like to thank, first of all, the organizers for putting up this brave effort in these difficult times. And I know how much, or only know partly, how much they're like fighting every day on both inside and outside running the school. So I would, so what I'm going to tell today is maybe try to motivate that while we scale up quantum computing or quantum information processors, I think it's also important to see how good can we use what we have. And in this particular case, I am more interested in exploring the space of a single qubit. And as I will show you that it is indeed possible to use the single qubit to perform things which are not possible classically, or in some cases, even in certain quantum scenarios. So here are two examples kind of taken from our recent work. One is the sensing. The other, which is we are also still learning, is machine learning. And the good thing is that being in CQT, we have people coming from computer science. So we get kind of infected by the language of computer science. So please bear with me as we go along to learn more about the possibilities that we have using single qubit for machine learning. Okay, so before I forget, I must say that the wonderful data that I will show you later is an outcome of a dedication of many people. Of course, those who are marked in red are the data that I will be showing today. There are other projects where others are involved and helping in running it. Of course, as you can imagine, nothing in the experiment would run if there is no fund. So we are funded by NRF as well as MOE for different projects. By the way, Dilip, if there are questions, do let me know. Yeah, I can stop any moment.
Okay, and one more thing. Would
Yeah.
you prefer audio or chat box?
Anything is fine. It's
Okay.
fine. Yeah, just if necessary, just stop.
Okay.
Okay. So what is it? It's a two-level system. As we know, it's a qubit. And in our case, we work with barium plus, Ba plus. This is roughly the energy level diagram you would often see. And throughout the school, those who had attended it have also seen it many times. This is more or less the same in calcium. You would find more or less similar in beryllium, a little bit different, but more or less you will see the same structure. And for us, the qubit is between S half and D5 half. So that's why we call it an optical qubit, because it is we need a laser. In this particular case, it's roughly about 2 micron, 1.7 micron, to drive this transition. And the other thing is that this is a D state is a very long-lived state. In our case, it's about 30 seconds, which is good and bad. Good in the sense that your coherence time of your qubit is very, very long. Yeah. The bad thing is that you need a very good laser to drive it. Fortunately, we have it. So what you see on the left side is a spectrum from this transition S to D. And you see, we get a line width of about 120 hertz. And this is mostly because it is magnetic field sensitive transition. So the magnetic field noise leads to this 120 hertz around clock transition. So once you have that, then you look at the other performance indicators. For example, the dephasing time. This is the Ramsey spectrum. The black curve you see is the Ramsey spectrum when our whole cycle of the experiment is locked to the line, which is 50 hertz. And the red one when it is not locked, which means that the 50 hertz noise somehow is seen, even though it is very small, is seen by the ion. And that leads to the magnetic field dephasing and leads to the decoherence or dephasing. But if we could lock it, of course, that means that the whole experimental cycle would be longer, but we can get to long coherence time or dephasing time. Our heating rates are relatively low. These heating rates, again, I would like to remind you about what Christian Roos had told you or Liefried has told you before. This is the heating rate that the ion sees because of God knows what, because we don't really know yet, but because of the surface effects or some technical noises. It is very low in our case, not because we have done anything great, but it's just because the trap is fairly big compared to where the surface effects come into play. The right side is the gate operations. These are single qubit gates, and what is being shown is randomized benchmarking to roughly tell you the number of errors that you gain as you run more and more gates. Of course, this is a very old data. As I will show you in the next section, the next meaning, it's two parts. So when I talk about more about the computing part, you will see that this has improved in the meantime. Then, of course, there is a focus on the scaling up as well. So what you see down there is a 30 qubit system, which is not, we do not run any qubit operations as of now on these 30 qubits. These are more for stability operations of the trap. However, we plan to do it in next few years. Yeah. All right, so in ion traps, you have also seen that apart from the internal states, the S and the D, which is the qubit, you have the external motion as well, which you have learned quite a bit throughout the school. I would not get into the details. In our trap, the dimensions roughly are about the R0, if you may like. The distance between the blades is roughly about 500 microns, so half a millimeter, and the end cap to end cap distance is about 1.5 millimeters. The trap is ran at a frequency of 20 to 25 megahertz with a voltage of around 1.5 kilovolts. Yeah. This gives a secular frequency of about 1 to 2 megahertz. So those are like the vital parameters for the trap running. Essentially, for what I'm going to say you in the next 15, 20 minutes has more or less nothing to do with the motional state. We do use motional state, but for what I'm going to tell you now, we don't need to know about the motional states. We'll mainly concentrate on the two-level system and on the qubit space. Yeah. Okay, so what I'm going to say now is divided into two parts, as I said. First of all, I will talk about the sensing application. What is shown here are just two levels. Now, if you have such a two-level system, you can use it as a clock, as I've shown you before. However, imagine that you have a background which is giving a noise to the ion, and it is a time-dependent frequency. So if you have a time-dependent noise, the goal here is to measure the amplitude as well as the frequency itself. Now, is there a measurement that we could follow, or a protocol that we could follow, which allows us to go beyond the classical limit of precision for the frequency measurement or the amplitude measurement? In other words, let's put it in the context. So suppose you have a B field and you have a spin. So we could write down the interaction as B dot S. Now imagine that the B is composed of a B naught and a B modulation, which is modulated at a frequency of small omega. What we intend to find is the B naught and the omega. Sorry, this is a mistake here. We intend to find the B mod and the omega. So the modulation amplitude and the frequency. And we want to know how small can the uncertainty be of these two measurements. Well, as we go along, I would only concentrate on the uncertainty on omega, but similarly, one could find the uncertainty on B modular. Okay, so the Hamiltonian, what we actually use is not exactly the B, but one could use the B. What we use is a sigma Z and omega D sine omega T sigma Z. So it's the same effect. The only reason we don't use the B is because for us, it's easier to have AC stock shift modulated rather than the B field modulated. Well, the question that we are actually asking is, there is a story related to it. And again, it's a private communication. I don't know how much it is true, but what I said was before the G-2 experiment on electron, when Demelt actually put up his proposal to the committee asked, as usual, you were asked for a scientific proposal to tell how long it takes to build the system. But he was asked like how long it would take to get the uncertainty down to 1 Hz. And his answer was 1 second, based on the scientific merit of it, even though that was not the intention of the committee. Now, the reason why it is 1 second is because if you think from the physical point of view, if you have upper state which has a energy uncertainty of corresponding frequency of 1 Hz, you would need 1 second to measure it to the level of 1 Hz. Yeah. That's the energy uncertainty principle that would tell you that. Now it comes from another direction as well, which is the quantum or information theory. So the variance of a parameter alpha, the alpha could be the B modulation or the omega in this case. The variance of that is, the minimum value of the variance is proportional to 1 over n, which is the number of measurement, and 1 over f alpha, where f alpha is the Fisher information, which is bounded by the Kramers-Rao bound. And this is, as you can see, this is a very, very important paper in information theory. And it goes back to 1945, published in Bulletin of Calcutta Mathematical Society. So the F alpha is actually the content of information that is present in a parameter alpha. And the quantum information, Fisher information, is given by this formula here, which actually tells you that how fast the state changes by a small change in alpha. So that's what the Fisher information tracks. And if you have a time-independent Hamiltonian, it is easy to show that F alpha is proportional to T square. And when you plug it in, you get the standard deviation to be square root of this, and therefore you get 1 over T. Okay, so the quantum Fisher information is this. Now, if you use a single probe, and the best thing to do is to use a superposition state, which is given by the probability amplitudes of probabilities of P0 and P1. So the Fisher information in that case turns out to be 4P0 P1 multiplied by the rate of change of the phase with the change of alpha, or the parameter. Yeah. Square of that. So which means you can maximize your Fisher information by creating an equal superposition state. And that's what we all know, because that's how the Ramsey technique works. And that's where it comes from. Now, if you think of the standard deviation or the uncertainty, it turns out to be the minimum uncertainty is 1 over t, assuming that you have only one probe or you have made only one measurement. Okay, there are various ways to beat it. And one of the simplest way is to increase the correlated. So these are uncorrelated measurements, n. Now, if you make correlation in the measurements or in the probes, you get 1 over n instead of square root of n. This is one way where entanglement helps. The other way is more trivial way. If your Hamiltonian has an explicit nonlinear time dependence or exponential time dependence, for example, e power t sigma z, you can show that the variance can scale as 1 over t power gamma. So what we are interested in is none of these. We would like to use one single probe, one measurement, and we would like to see for a time-dependent measurement whether we can scale faster than 1 over t square, or 1 over t. Well, in order to do that, the first thing to do is to ensure that we are limited by the statistical uncertainty, not the systematic. Because if we are limited by the systematic uncertainty, there is no hope to see the scaling. In order to ensure that, what is plotted here is the number of measurements as, so the phase, the uncertainty in the phase measurement for our qubit as a function of the number of measurements, independent measurements taken. And you see that this scales as 1 over square root of n, which means up to certain time, we do see limited systematics below the statistical uncertainty. So this is the regime where we will work at. Now, what is the standard technique? I'm just repeating, Christian Roos has already told you before, but just to make things complete, what you start with is an initial state of 0. You create an equal superposition of 0 and 1. And once you are in the equator of the Bloch sphere, there is free evolution of the atomic qubit. And at the same time, the laser is also evolving in the same plane. Now, if there is any noise which leads to a lag or a faster change of the atomic qubit or the atomic state, which is given by the red arrow here, this phase between these two is what we measure in an experiment, and that's this phi alpha. Of course, the sensitivity of that measurement also depends on which final state you project it to, and the choice of the final projection is also important. So that's the general technique, Ramsey technique, which is followed for any clock measurements or any phase measurements. All right, now if we apply and do the same for this Hamiltonian to figure out the frequency small omega, we would end up in a quantum Fisher information that scales, as you can see, with the number which is somewhere 1 over t, provided you have measured it at certain particular time, or in this case, time is written in a slightly different manner. But in each of these oscillations, you only get to 1 over t, provided you could measure it at certain particular times. Okay, so what are the ingredients? The ingredients are that we need to start with the equal superposition, and then we have to project it such that we get maximal information out. Now, in this particular case, as you can see, the Fisher information, if we calculate it out, is the difference of these eigen values of this Hamiltonian, which is oscillating with time. Now, if you look at this difference of mu max at any point t, at any time t prime, minus mu mean any point t time, this is roughly 0. And that's the reason why you would not see much of an increase in the Fisher information, and hence your uncertainty will be scaling only 1 over t. but only few cases where there is a small change between the first cycle to the second cycle. So there was a proposal forwarded by Pang et al., Pang and Jordan in 2017. And the nuts of it is that one way to enhance it is by changing the sign of this minus to plus in every cycle. How do you do it? You apply control pulse at the antinode of each of these eigenvalues, which means those who are familiar with spin echo, in a spin echo, your purpose is to remove the noise, and therefore before it crosses, you flip by pi pulse to the other side. In this case, it's just the opposite, because you want to increase the phase gathering every cycle, which means your pulse sequence is now have to be shifted by pi by 2. And which is this sequence just tells us. So this is again the same thing. We run first the equal superposition state, then the qubit evolves, and as the qubit evolves, we perform this feedback mechanism of applying a pi pulse every pi by 2 of the cycle. And if we do that, then we could actually gain more information in the same time. Now, how does that scale? So in order to do that, this is just the determination of the gradient of the change of phi as a function of alpha, in this case, the omega. So we change the omega, which is in this case given by f. As a function of f, we see that the phi changes, and these are measurements done repeatedly to get the uncertainty lower. The slope of this gives us the quantum Fisher information. If we now plot the slope where the red dots are uncontrolled, where we have not applied the pi pulses, we see a scaling which is 1 over t. And this is not surprising, that's what we would expect. But when we apply the pi pulses, we see that the Fisher information, which is just the inverse of the uncertainty, scales as 1 over t square up to a time of about 80 microseconds. And after that, the systematic starts to play. In this case, the decoherence of the system when we run very fast single qubit rotations. And this has to do mainly dominated by the instability in the laser power. Each of these the get time is about 1 to 2 microseconds. All right, so that's the original paper, and then very closely related but not the same is where you have nonlinearity in the Hamiltonian itself. Then you can actually use that nonlinearity in order to develop what is called Lockin Amplifier, which is partly classical and partly quantum. While there has been one experiment on superconducting qubit to get a scaling very close to 1 over t square. However, if you use a superconducting qubit, the difference is that the ion is sensitive to an external field. And that's where our interest comes in. Because if you look into literature for the dark matter search, you will end up in something called axion-like particles, dark matter, and these are light mass. In fact, it is claimed that these particles are flowing through us, we just don't realize them, and it should be flowing also through the experimental apparatus, including the ion. Now, when it flows through the ion do see a classical field, which is more or less given by this term here, where you see there is a time-dependent part and the sigma E, which is the either the spin of the electron or any of the angular momentum of the electron that couples to it. So if we apply that technique and look at the limit that we can get even with a single qubit, we end up somewhere here. Now, the interesting, so what is this plot tells us is that this tells us what is the coupling strength that we would expect if we would have seen a signature at a given frequency. Frequency here corresponds to the mass of the action-like particles. So that's given by the color code here. So the lower coupling, which is around the blue, is where things becomes very interesting in terms of the new physics. We stand here. However, I must say that there is till date no direct measurement of the electron coupling to ALP particles, because this coupling constant GAE is different from those of the nucleonic coupling. Now, one could actually use the same technique and the protocol to enhance by increasing the number of atoms, which certainly is not a possibility for ion traps, but could be a possibility for a gas cell, for example. On the other hand, the coherence time may be compromised in that case. Okay, so is there any question up to here? Okay, so I don't know if I don't hear or you also don't hear.
We can hear you. Looks like
Okay.
there are no questions.
Okay, perfect, perfect. Sometimes, you know, I would be keep speaking, but
yeah.
Okay, good, good, good. So I would then switch topic from here. And this is a little bit of big switch, I would say. So now I'm going to tell you that single qubit is also very, very good to be explored in terms of machine learning. Now, here is a kind of a pictorial depiction of a quantum computer, if you may like, or a quantum circuit, if you may like. Each of these are qubits, and they this is time. You start by doing single qubit operations on them, and then 2 qubit operations, and then again single qubit operations, and so on. So that's the depth of the circuit, and this is the width of the circuit. Now, there is also the color code here. As you go in depth, you see that it becomes hazier because there are errors that comes in, and that's where we are presently at. It's called the NISQ era. So these are noisy devices. Now the question is it good to go this way, or is it good to go this way? Ideally, it is good to go diagonally, meaning having both. Yeah. So our present, just our own present interest is actually probing more on the depth and finding out problems which might be interesting. Because if we understand that, we could eventually go on the scaling, even with a smaller number, to see certain problems which could be interesting and can have certain advantages. So what I'm going to tell you about is classification problem. Now, classification is a problem which is everywhere. We can't avoid it. And it starts when we are very young, right? So this is a task given to my kid some days back, which asked him to circle the living things here. Now, well, a human being, he would, after a few trials, would eventually...
Also, I'm not able to hear you.
Are you not able to hear me? Oops. Is it better? Hello?
You are audible to me.
Oh, I am audible. So then it's Dilip's problem. Okay. Okay, Good. You see, a child or a human being would be able to eventually classify it by looking at it and learning from it, and then able to apply his learning to understand what is living and what is non-living. Now, if you have to come up with an algorithm to do it, this would, or this actually is existing. It looks like this. You find the features that are associated with each of these objects, create a feature vector space, and then use this, this vector space to apply certain planes to see that you can distinguish between different features in the vector space. And this is presently done by several means. So the first one is a very widely used classical compute, which is called a state vector classifier. You could have neural networks like convoluted neural networks, or nowadays what is most relevant is a deep neural network. Well, the purpose is that there are two parts. You use these to look into the feature space and then distinguish in the feature space the different types and classify them. And that's it contains two parts. One is the learning or the training part, where you give data and the machine learns, and then it uses for verification. Now, if we look into a little bit deeper into the neural networks, we would be able to understand where the problem comes there. So this is an architecture of a neural networks. Each of these are the neurons where certain compute happens. And it gets input from the previous nodes. These are called the hidden layers. You can have one or many of these layers. Now, what is actually done in this hidden layer is the following. You take the vectors from the previous one, V prime, put some weight A and B, and calculate a nonlinear function of what you have been given at each node. So now, if you do that, then keep on doing it, you should be able to eventually get a target function which mimics a particular class. And that's how you distinguish between different class, by changing the weights. And this is the training part of it. Now, it is information theoretically, it is possible to show that even a single hidden layer is, in principle, a universal classifier. However, the problem is, in order for complex classification, this requires you to a very large number of these nodes, very large meaning infinitely large, in order to classify complex problems. So we also know that some of these complex classification problems are NP hard. Now, last year, Jose Latorre and his group came up with a alternative where, so I must say that there are alternatives also on a state vector machine which could use quantum. However, we are looking into only classifier based on what is called a data reuploading. Now, in this case, the concept is very simple. You start by encoding the data that you have, the classical data from the feature space, into the qubit space by the rotation angles, and that's given here. Xi is the data. You apply some weight to it, and then add some weight, and you have a unitary operator, and then you apply these rotations sequentially, but you have to ensure that each of these rotations are non-commuting. If you do that and then train your machine by changing these phi i's and theta i's, such that a given set of data which belongs to a particular class ends up in a particular point or close to a particular point in the Hilbert space that you are looking at. More or less, looking at this is the following, that you have your data tells you how you rotate in the Hilbert space, but then all the red dots would end up in here, while the blue ones would end up in here. That corresponds to class B, and this corresponds to class A. Well, let's look into, this is a very preliminary data. We started working a couple of months back, and then we see, what you see here is a very simple problem where we intend to separate classes which belongs to the center of the circle or inside the circle and outside the circle. And the left side shows the simulation, because you can, we are not telling anything which is not possible by classical computers. Of course, it's a single qubit, you can simulate it. And if you do that, you get this. On the right side, you do it on the actual quantum processor, and you end up in this classification. Of course, a circle is relatively simple if you think of the symmetry of a qubit. However, we looked into more complex classes. This is a 4 class. And what is more important is it a non-convex boundary. This is a non-trivial problem, and it is considered to be NP hard. However, we see that that this single qubit can distinguish it very well. Yeah. We also have done what is called supervised learning, meaning we optimize the space of the optimal values of the training data set, and we ended up, you see the red dots are where we initially started it, and the minimum value of our error function ends up in here, while in this space it ends up in here. Of course, what is more important is that when we have big data sets with many parameters, it is the feature space becomes higher dimensional. And this is one example where we start to see the limitations. And this is with one single layer, and then you—
Hi, Manas, you have 10 minutes.
Okay, I am nearly close to that. Okay. So when you have a hypersphere, this is a 4-dimensional feature. And what we intend to see is that, are we able to classify those which are inside the hypersphere and those which are outside? Now, it is not very easy to actually to show it in figures or in graphs. So what we did here is a histogram of the points which are within a certain radii. Now, if you see that with one single layer, the overlap region tells you the error in our classification. If we increase to 2 layers, it is better. In 3 layers, it's even better. And in 4 layers, we are nearly there. And at present, we are trying to see that how far we can go. Okay, so that brings me to the conclusion. So what I tried to convince you with is that with a single qubit, you can go beyond the standard quantum limit, which is given by the red line here. And you can do particularly noise frequency measurement that goes beyond the standard quantum limit and scales as 1/t². With the same single qubit, you could actually do classification of data. And as a kind of side note, we most often talk about scaling in terms of either speed or in terms of the number of qubits. However, we tend to underestimate that at present our classical computational limits are because of the energy consumption. And in this particular case, what we are really looking into is the possibility of using the nonlinearity of the qubit to substitute, for example, a deep neural network for which the node calculates the nonlinear function, which requires substantial large number of resources, could be done without much effort with a single qubit. So that is more or less the take-home message that I would like to convey. I am done with this. Thank you for your attention, and I would love to take questions if there are any.
Yeah, so we have time for a few questions. So if anyone wishes to ask a question, maybe you can unmute yourself and then ask.
Yeah, hi, this Saikat. I have a question.
Yeah.
Yeah, Manoj, so regarding the earlier part of the talk for the detection of axions.
Yeah.
So that part I was a little confused. So how your phase precision relates to axion? Do you have a so is it?
Yeah. So you see here, right? This is the Hamiltonian, which is substituting the Hamiltonian of what I showed before, which is the here. So when you have the background action field, right? This is the action is taking place of this, and the omega is the mass of the action.
So that's the question I have. Is it taking place of this? It's added to this, right? So the question is really the relative ratios of the two Hamiltonian. You still have this evolution.
Right. Of course, we did not see anything, right?
Yeah, but the question is really how can you separate out this free evolution or the usual unitary to actually extract that small little.
Right. So what you do is you change the frequency, right? So if you are in resonance, you would see it going up because the mass is a very, very unique mass. But this frequency which you apply from outside is what you scan.
Okay. Yeah. So your Fisher information still is parameter dependent.
Yeah.
Like that's so basically where your Fisher information is optimizing or maximizing is also where you would like to have this dark matter interaction to be optimized. Right?
Yes. That's right.
So does that require any special tricks, or is it just?
No. So the problem is if you really have to scan over a large mass range, then this is not the right technique. So usually what you do is if you see a signature without applying the pi pulses, then you can improve on the uncertainty.
Okay.
So you need to have some idea what you are looking for. Yeah? Now, having said that, if you look into the other work done by Ozeri, which is Lockin Amplifier, you could actually combine this with the Lockin Amplifier to get to that value.
Okay.
Yeah.
And from this part's conclusion, the plot you presented with N and T, and ideally this in the Fisher information also N and T are equivalent, right? Like either if you can have a good coherence time, if you may wait long enough on a single spin, a single ion, that's equivalent to short measurements on many ions.
Yes. That's right. So the right. So the N and T play the same role, right? More or less, yeah. So let me go back here. Yeah, so you see here the N and T, they play this similar role here. So you can enhance by this and you can enhance by this as well. So the ideal situation would be if you have correlated measurements and also long coherence time. So you enhance here to make it T square maybe, and here also N, which is not square root of N.
Yes, so any other questions? Yeah, looks like Manas, we don't have other questions. Here I have just a query regarding the machine learning. So essentially you're using this single qubit to identify quantum system, right?
Right.
Are there some limitations or are there some constraints as to what kind of quantum systems it can?
No. Dilip, maybe there is.
I missed something. Yeah.
Right. So we are not doing classification of quantum states. We are
Okay.
doing classification of classical data,
All right. Okay. Okay.
but using quantum bit.
Okay.
So the machine is quantum, but the data is classical.
Classical. Okay.
And it is also not trivial. I did not mention it, but it is not also trivial how we know, like, we're trying to understand now, like, how do you load classical data into a quantum machine? It's not a trivial thing at all.
Yeah, there are no other questions. Okay, so Manas, we don't have any further
Perfect,
questions.
perfect.
So thank you so much for a
Thanks.
very good talk. Yeah.
Nice to see you.